Looking at section 3.3, part 2, in the same way we were able to expand a logarithmic expression, we can also condense a logarithmic expression. So a little review of those rules that we reviewed in terms of our exponential rules that we then turned into our logarithmic rules. When we talked about the product rule, we said if we were to multiply two pieces, we can turn it into an addition. So now we're just going to go backwards. So if we see a log with the same base, we can take those two pieces, the m and the n, and we can multiply them together. The same way we looked at our quotient rule, whenever we had that division, it told us that we had to use subtraction. So if they give us a subtraction of a log with the same base, we can turn that into a division. And the same way that we had when we had our exponent on the outside over here on the right-hand side, we dropped it down to the front. Now we're going to take it from the front and we're going to throw it back up into an exponent for our power rule. So all we're doing is kind of reversing those orders that we did before. So let's take a look at a couple examples. It says to write as a single logarithm. We have a log of 25 added with a log of 4. That means we can take, since these are both base 10 logarithms, our regular logs, we're going to end up with a log of a 25 times 4, which gives us a log of 100. And if we have that base 10, what's the log of 100? Well, 10 to what power is 100? 2. So our final answer is just going to end up being a 2. If we look at the next one, we have log of that 7x plus 6 minus the log of x. So again, we have that base 10. That means we have a subtraction is going to turn it into a division. That means that we're going to end up with the logarithmic function of, on the top, a 7x plus 6 divided by x. Now remember, don't confuse yourself with that plus sign. This plus sign in the middle here of that 7x and that 6, that does not allow us to separate it. Anything. This is a whole logarithmic function, so don't try to take that out. And then the last one has 2 natural log of x, or 2 ln x, plus we have a 1/3 ln of x plus 5. So I see some numbers that are in the front, so that means we can use our product rule to throw those back up as exponents. That means that we're going to end up with the natural log of x squared added with the natural log of this x plus 5, which is to the 1/3 power. Well, if we have an addition, we can turn that into our multiplication, which means we have ln of, I guess I don't really need the parentheses, I just call it an x squared x plus 5 to that 1/3. And then that 1/3 is just not simplified. We need to make it into that final answer where we turn it back into the cubed root. So that means our final answer, we're going to have an ln of x squared, and then we're going to have this 3rd root of an x plus 5. So the change of base property, it says for any logarithmic bases a and b, any positive number m, we can change the base of a logarithm by using this method. It says log base b of m is equal to, we have log base a, so we are now giving it a new base, right? A new base. What base do you think we might want to go to? Probably a base 10, or using those natural logs, we can go to a base e. So we're going to change the base into a log, they call it a. So log a of m. So whatever we were originally taking the logarithm of, that's what's going to the top, the numerator of our fraction. And then we're going to take log base a of whatever that original base was. So it says that the logarithm of m with base b is equal to the logarithm of m with any new base divided by the logarithm of b with that new base. So whatever you're changing your base to, it has to be the same value. Now, if you kind of think, just a little way of remembering, if you've kind of let this stuff stick, this b is the base goes to the bottom. That might also help you in terms of which one goes on top and which one goes on the bottom. So in general, it says the change of base property is the introduction of the common and the natural logs. So again, I said base 10 or base e. So if we go to this base 10, that's where we have that log b of m is going to equal log m divided by log b. Because we change it to a base 10, we don't have to write that in. The natural logarithms, that's where we would have had our natural log, right, our ln, or using that concept of the number e, right, our natural logs ln of m divided by ln of b. So let's look at an example. It says use the common logarithms to evaluate. If I have a log 7 of 2506, they want us to use the common logarithm, which is going to be changing that to that base 10. Common logarithm, that's that base 10. So that means we are going to take the log of 2506 and divide it by the log of 7. And all you have to do is grab your handy dandy calculator. And let's see if this will pick up okay. So log of 2506 divided by the log of 7. What do we get? 4.02-ish. So now I can figure out that that's going to be 4.02. It gives me a numerical answer. Can move this over to the side just a little bit. And let's look at one more. What happens if we were to take that same thing and change it into that natural log? So if we go to the natural log, that means that we're using our ln. So if we have a log base 7 of 2506 and we were to change that to an ln of 2506 divided by the ln of 7. So now if I were to try to make this an ln, it's not going to do it. I'll just rewrite it. The ln of 2506 divided by the ln of 7. We got the same exact value. So we still get a 4.02 in the end. So it shows that it doesn't matter whether we change it into our base 10, our common logarithm, or we change it into that natural log. In the end, when we do that division, we ended up with a 4.02, which is the same value.